Okay, we are going to be talking about section 4.5, applied optimization. We are going to use optimization in word problems. I'll tell you how you would do that. Solving applied optimization problems. First of all, what you would do is read the problem carefully, and you want to make sure that you understand the problem right, and note down what is given in the problem. What is the unknown quantity to be optimized? We have to determine that. Next, you are going to draw a picture. Drawing a picture is solving the problem, solving half of the problem. So be careful about labeling any part that might be important for the problem. And then next, you're going to introduce some variables. You're going to look at the picture. You're going to look at the problem statement, and you're going to list every relation that you could see and try to express them as an equation or algebraic expression, and make sure you identify the unknown variable. Next, we are going to write an equation for the unknown quantity. So in the step 3, we may have more than one equation. In step 4, we are going to kind of combine these equations that we had found in chapter 3 and end up with a single, with a function or an expression that contains the unknown of a single variable, or maybe in two equations into unknowns so that you can solve it. Okay, this may require some manipulation on your side. And then number 5, we are going to work on this function, and we are going to find the critical numbers, critical points. We are going to test the critical points and the endpoints in the domain of the unknown, and you can draw the graph of the function that you have in hand, and you're going to use the first and second derivatives, and then build up your, if you need, you can build your tables as we did before, and then come up with the maximum and minimum values that you're asked to find. Okay. For example, we have this question. There's an open box. First, a picture. Let me see just a sec. Where's my mouse? Okay. So this is the open box. If you just these sides are actually, it was first a square, right? 12 by 12, and then the corners were cut, and you can just fold it, and you form an open box out of that. Okay. And the question is, what size corners maximize the box's volume? We are interested in the volume. What's the volume? This side times the height. Okay. Width, length, and height is going to give you the volume. But before we do that, we have to express what this length is. So we are interested in this length. And since the squares were cut on the corners, we call them x's. So this length is going to be 12 minus 2x. Okay. So as you would see in the picture, 12 minus 2x. And then the height is x because of this. Okay. And then this is 12 minus 2x as well. So what you would do is you're going to multiply them all. As you would see in the second picture, this y is going to be the volume. Volume is x times 12 minus 2x squared. So this is the function that you are going to maximize, because they're asking about the maximum volume. And what's the domain of this function? The domain of this function is at most, it could be, how would you find it? You can equate this x's to 0, so x is 0 and this is 0. You get 6 here and you get 0 here, so x could be between 0 and 6. It cannot be bigger than 6, because if it is bigger than 6, if you go back to this, if x is bigger than 6, let's say 7, this is 14. 12 minus 14 is negative number, so the side of a box cannot be negative number, so the domain has to be between 0 and 6. Next, what we would do is we are interested in this function, its maximum and minimum. Here's the picture is given. Of course, you don't have the picture given. So what you could do is you can draw it by yourselves, or you can use the steps that we discussed. You take the first derivative and second derivative, and you find the intervals where the function is increasing and decreasing. If you do all these, you see that between 0 and 2 it's an increasing function, 2 to 6 it's a decreasing function, and it's concave down until some point here, I guess, right? They don't say it here. Concave down, and then it becomes concave up here. But we are interested in the maximum value of this function, and maximum can be obtained at 2. Okay, that's how we would do that. This is the second example. In the second example, let's see, I'm going to read the question from our book. So you've been asked to design a 1-liter can shaped like a right circular cylinder. So this is the 1-liter can that is designed. Okay, what dimensions will use the least material? Okay, when after you graduate as an engineer from the school, when you start working, you're going to start. You may work in the production area of a company or factory, and then they may ask you to build a cylindrical, a cylinder like that, a can that's going to take the least, that's going to use the least material, because they want to save money from the, from the cost of the material. And you can think that this question is suitable for such a situation, and you can immediately use your calculus information knowledge to come up with such a computation and the result. So what is given, excuse me, okay, it's kind of windy outside, and I'm a little bit cold, I guess. Okay, so at first, so we are interested in the material, right? So in that case, we have to calculate the surface area of the material. Okay, and then we want to minimize the surface area so that we are going to use the least material. So we are going to just give some, we are going to label the variable. So h is the variable, the radius or the diameter, the radius is r, the diameter is 2r, and then we are going to write the surface area of this material. So our can, 1-liter can, could be like this, or it could be like this. It could be short and wide, or tall and thin. So we are going to see for which r, okay, or for which h, doesn't matter, we are going to get the least material used. So this is the area that we come up with, but how would you write? So we have circles here, down and up in both. Let's use just this one first. Pi r squared is the area of top, and pi r squared is the area of the bottom. So we have two of them. So 2 pi r squared is the surface area of the areas of the circle discs here. And then we have this this side, and it's actually, when you open it up, it's a rectangle. This rectangle has the area as circumference of this disc, okay, or circle, times the height. Height is h, and the circumference of this is 2 pi r, right? 2 pi r h, okay, 2 pi r h, and so this is our surface area of a can. And what's the constraint for us? they want the volume to be 1 liter. This is our constraint. What is the volume of such a thing? It is the base area times height. Base area is pi r squared times height. Pi r squared times h has to be 1 liter. And 1 liter is 1000 centimeter cubed. So I can write a relationship between h and r from there. So pi r squared h is equal to 1000, and then h is equal to 1000 over pi r squared. So we continue writing, okay, and we also write the area of the side, which is actually 2 pi r times h, 2 pi r times h. So instead of h, I am going to write, I'm going to write 1000 over pi r squared, and we have some r squared cancelled here, and at the end we have this 2000 over r left because 2 pi r times 1000 over pi r squared is going to give us, pi r's are going to cancel, and we have 2 times 1000, which is going to give us 2000, and then there's r left in the denominator. So as you will see, this is the function, okay, optimization function, and in terms of only one variable, and then we just work on this function now. We take the first derivative, second derivative, and try to find the critical points if there is any. Actually, when you do that, you get a critical point as this number, cube root of 500 pi. And you apply the first derivative test, second derivative test, and you see we have concave up everywhere, and it is decreasing till this point and increasing afterwards. And by applying the test, you get a minimum at that point. So the minimum surface area is going to be attained at this point, which is going to be, let me see after calculation, the number wise. Okay, actually this number here, if you compute, it's close to 5.42. And then, okay. So we can actually, it doesn't say how much the area would be, but we are going to say that such a cylindrical can is going to have is going to use the least material when the radius is going to be this much, and the height, we can just find the height by using the relationship between height and radius, and then we get that 10.84 centimeters. Okay, so that's how you get that. So the middle steps is not shown here, but you can fill it up easily. Here's another example. This example is example 3 in our book. A rectangle is to be inscribed. So we have a semicircle. A rectangle is put inside the semicircle. This is called inscribed in the semicircle of radius 2. And what is the largest area the rectangle can have, and what are its dimensions? Here, the rectangle is inscribed in the semicircle, right? And we want the largest area the rectangle can have. So what we are going to just draw, we first draw a semicircle, and then we draw a rectangle inside, and then we just give some names x's to this side because we don't know it. Okay, whenever this is x, we can find the y coordinate by looking at the semicircle. X squared plus y squared is equal to 4 is a circle. But if you isolate y from here, y is square root of 4 minus x squared, right? So this is the this length, width of this rectangle. So width is square root of 4 minus x squared, and length of the rectangle is 2x, because x here, it makes it 2x. Okay, and then we just calculate the area. Area is 2x times square root of 4 minus x squared, and we have a function of the area, and we just a of x, you can call it a of x, and then work on this optimization function. Okay, and now you take the first derivative, second derivative, and you're gonna find then you take the first derivative, you get such an expression. You get actually x is equal to minus plus square root of 2, and also x is equal to minus plus square root of 2 is a critical point, but let's check whether it's in the domain. X is equal to plus minus square root of 2 is close to 1.4, and 1.4 is less than 2, so it is in the domain, so that's fine. It's a critical point. Okay, and then we have the endpoints, because x can take maximum values negative 2 to 2, and we have endpoints as well. Alright, or maybe we should say x goes from 0 to 2, so let's, yeah, x is between 0 to 2, because we have negative x here, right? So the endpoints are 0 and 2, we check those endpoints as well. Critical points, if you put them in area, you get 4. The endpoints, if you put them in a of x, you get 0 and 0. So the maximum value is 4. So the area has a maximum value of 4 when the rectangle has square root of 2 units high and square root of 2 units long. Okay, so we find it. Alright, and that's the solution to this question. And I'm gonna skip this example, and we have an example from economics. I'm gonna also skip that. You can find it in our book, and that's it. Thank you.